Welcome to Factoring Polynomials with a Visual Guide. This is the first of a series of videos to help students understand factoring polynomials completely. In this part of the tutorial series, we will be discussing factoring polynomials using the greatest common monomial factor. But before we continue, these are important concepts you might want to recall. If you need to review these topics, or you are confident enough to skip to other parts of this video, click the links in the description below. But don't worry, we'll try to explain them naman as we go along. Factoring polynomials is a critical concept and is key to understanding future topics or subjects like intermediate algebra, trigonometry, calculus, and, believe it or not, even some topics from the science subjects like physics and chemistry, and more. Yup, you can say that factoring is really important. Sa madaling sabi, wala kang takas dito. Searching Google and YouTube on techniques and methods may seem easy, but actually has scattered information that may leave many students confused. Others may find factoring to be frustrating, and some may even say, it's a jungle in there. So, to help us navigate through the very thick jungle called factoring polynomials, here is our solution: a concept map. Our visual guide to factoring polynomials. Okay, I know, this still looks confusing. But in this series of tutorials, we will go through each method, part by part, figuring out and learning the concepts through examples and exercises, and hopefully master factoring polynomials in the process. Don't worry, a link to a printable version of this visual guide is in the description below. Okay, we can now start learning how to factor polynomials completely. The very first step when you're asked to factor is to get the greatest common monomial factor, or GCMF first, which is our lesson for this part of the series. Look at our map. We are currently here. Let's not overwhelm ourselves and let's focus on this part. But as we proceed, let's quickly recall a topic called prime factorization. Remember that prime factorization is finding all primes that when multiplied together will make the original number. Also recall that a prime number is a number that is only divisible by 1 and by itself. Let's review prime numbers by listing some of these numbers. On this part, we'll write the composite numbers. Let's start from the smallest. Note that 1 is neither prime nor composite. So the smallest prime number is 2. It's divisible by 1 and by itself only. Then 3 is prime since it's divisible by 1 and itself only. 4, aside from divisible by 1 and itself, is also divisible by 2. So it's composite. Using those criteria, we continue the list of numbers. So 5 is prime, 6 is not, 7 is prime, 8 is composite, 9 is not since it's divisible by 3, 10 is composite, 11 is prime, and so on. Now, going back to prime factorization, let's say we're asked to get all the prime factors of 24. There are a number of ways we were taught to do this. One is using a factor tree, wherein we just write two numbers that multiply to the number and continue branching out until we end in a prime number. Let's quickly try that. 24, we know, is 3 times 8. 3 is prime, so let me encircle that since it's the end of the branch. Looking at 8, we know it's 2 times 4. Since 2 is prime, let's encircle it. We are now left with 4, which is 2 times 2, which are also prime numbers. So, looking at our tree, the prime factors of 24 are 3, 2, 2, and 2. If we multiply them together, the product is 24. Another method is called continuous division. Let's do this by drawing 2 columns like so, and putting 24 here. Let's think of a prime number that exactly divides 24. Since we have a list here on top, let me use it as a guide. It's best to start checking the divisibility from the smallest prime, which is 2. We know 24 is divisible by 2, so write 2 here. Dividing 24 by 2, it's 12. Write it here. We check divisibility again. 12 is divisible by 2, therefore 6. 6 is divisible by 2, therefore 3, which is of course now a prime number. Hence, looking at these parts of the table, the prime factors of 24 are 2, 2, 2, and 3, which is exactly the same as the other method. But what we really like to recall is how to do continuous division, but writing the factors in a row instead of writing in columns like in this part. Okay, let's start from 24 here. Then using again our list of prime factors on top, we know 24 is divisible by 2. Write 2 here. 24 divided by 2 is 12, but we don't need to write 12. Just remember the quotient 12. 12 we know is divisible by 2. Write 2 again here. 12 divided by 2 is 6. But we don't need to write that quotient 6. 6 is divisible by 2, so write 2 again. 6 divided by 2 is 3. Write 3 down since it's a prime. Thus, we end the list of prime factors of 24. Take note that the prime factors we got are consistent with the answers we got from the other two methods. Also, take note that the arrangement of these numbers doesn't matter. Because multiplication is commutative, they're all equal to 24. Now, let's recall applying prime factorization to get the greatest common factor of numbers. I know some can do this mentally, but let's still do this because this skill will be very much needed in future topics in algebra. Let's look at this example. We are looking for the GCF of 18, 45, and 63. Let's write the numbers on the right side like so. And then, list all their prime factors. Let's start with 18. 18 is divisible by 2, so let's write 2 here. 18 divided by 2 is 9. 9 is not divisible by 2. However, 9 is divisible by 3, so we write 3 here. 9 divided by 3 is 3, which is already prime, therefore, write 3. So, for 18, we have the factors 2, 3, and 3. Now, take note that when using prime factorization to get the GCF, aside from writing the prime factors, we should align common prime factors. So let's apply that, and this time, let's break 45 into primes. 45 is not divisible by 2. However, it's divisible by 3, so let's write 3 here. But, as we said, let's align common prime factors, so put 3 here, aligned to the 3 on the upper row. 45 divided by 3 is 15. 15 is divisible by 3. Again, write 3 here, aligned with the 3 on top. 15 divided by 3 is 5, which is already prime, therefore, write 5, but on a separate column this time. So, for 45, we have the factors 3, 3, and 5. Lastly, let's quickly break 63 into primes. 63 divided by 3 is 21. 21 is divisible by 3, so write 3 here. 21 divided by 3 is 7, which is already prime, so write 7. So here are all the prime factors of the numbers 18, 45, and 63. Now, The next step is to bring down all complete columns of factors. So we have this column and this one. Bring them down, so we have 3 and 3. Multiplying them, the GCF is therefore 3 times 3 or equal to 9. Of course, as we said earlier, some of you can do this mentally, confidently, so you can skip prime factorization and write 9 immediately. But again, knowing this process will be valuable in the long run. So, let's have some exercises, and we're asked to get the GCF of the following. Yup, using prime factorization so you can practice. You can pause this video now and work on them. Don't worry, the answers will be shown in a while. Kaya yan, go! Here are the answers so you can check. Now, let's apply these very same concepts to polynomials. This time, instead of looking for the greatest common factor, we are now looking for the greatest common monomial factor. Finally, we have come to our lesson. Let's look at our example. How do we get the GCMF of these two monomials? How do we do it this time that we already have variables? Let's focus on the numerical coefficients first and list down all their prime factors. 21 is 3 times 7. Negative 28 is 2 times 2 times 7. But since we have a negative sign, negative 1 is also considered as a factor. Now, let's move on to the literal coefficients. We expand them by using the definition of exponents. X squared means x times x. Write them here. Xy cubed means x. Align it on the x on top. And y times y times y on separate columns. Bringing down all the complete columns, we have 7 and x. So finally, the greatest common monomial factor is their product, 7x. But we're not yet done. Let's answer the next question. Finally, we are factoring. So, how do we factor the binomial 21x squared minus 28xy cubed? Recall that when we say factor, we need to look for some values that when multiplied will make a specific value. So, the first step is we write the GCMF of the two terms in our polynomial. However, do these terms look familiar? They're actually the monomials in our previous example. Therefore, we already got the GCMF. It's 7x. Write it here, and it's already one factor. Now, how do we get the other factor? The one that we need to multiply the GCMF with to get our polynomial. Let's look at it one term at a time. What do you think should we multiply 7x with to produce 21x squared? By quick analysis, it should be 3x. Write it here. But another way of getting it is to simply use the opposite of multiplication, which is division. 21x squared divided by the GCMF 7x is 3x, which is the same as we got earlier. Next, what should we multiply 7x with to produce negative 28xy cubed? Doing it mentally again, it should be negative 4y cubed. Or, another way of getting it is by dividing these terms. Step by step, carefully, negative divided by positive is negative. 28 divided by 7 is 4. X divided by x, we cancel. Y cubed divided by 1, because there's no y in the GCMF, is y cubed. Hence, the other monomial is negative 4y cubed. Again, the same as what we got earlier. Finally, we have the values that when multiplied will have a product equal to our polynomial. They are the GCMF 7x and the binomial 3x minus 4y cubed. It's a good habit to check, and we can do that by distributing the monomial 7x to this binomial. Let's try. 7x times 3x is 21x squared. 7x times negative 4y cubed is negative 28xy cubed. Our answer must be correct. Therefore, we can say that these are the factors of our polynomial. Summarizing, to factor a polynomial by GCMF, the first step is to get the GCMF first. The second step is to divide the polynomial by the GCMF so you can get the other factor. Finally, it's a good habit to check by multiplying the factors using the distributive property. Let's have some exercises. Get the GCMF of these terms and factor the polynomial. You can pause this video now and work on them. Kaya yan. Go! Here are the answers so you can check. But before we go to our next set of exercises, let's look at the second factor here, the quantity x minus 5y cubed, which we know we got from dividing 3x cubed y minus 15x squared y to the fourth by the GCMF 3x squared y. Let's look at x here and compare it to our prime factorization here on top. What do you notice? Observe that x is the only factor left not brought down to get the GCMF. See the pattern? Now, let's look at the second term, negative 5y cubed. Observe also that these factors not brought down all multiply to negative 5y cubed. So prime factorization and expansion of the literal coefficient does not only give you the GCMF, but it can also give you the terms of the remaining factor. However, prime factorization can be tedious. Expanding is still easy in this case because the maximum exponent of our variables is just 4. Can you imagine expanding y raised to the 50th power? Writing the variable y 50 times is so impractical. Hopefully, we can find an easier way to do it. Let's go back to the process of prime factorization here. Looking at the numerical coefficient of the GCMF, which is 3, well, it can be solved mentally by some. No faster technique there. You can do it faster by practicing. Let's focus on the literal coefficient of our GCMF instead. Observe the first variable x. Our GCMF is x squared. Is there a way to get it by just looking at these? Observe the variable y next. Our GCMF is y. Is there a way to get it by just looking at these? Do you see a pattern? Notice that the exponents of the variables in our GCMF is equal to the smaller exponent between the same variables. Meaning, when you look at the variable x here, the smaller exponent is 2, therefore the GCMF is x squared. Also, when you look at the variables y here, the smaller exponent is 1. Therefore, the GCMF is just y, with 1 as the exponent. Thus, there's really no need to expand the variables. Simply choose the smallest exponent of the variable. Further implication of this is, If you can get the numerical coefficient of the GCMF mentally, there is really no need to do this part. Just use our shortcut and choose the smallest exponent. Here's exercise 4. We make it more challenging by giving 3 monomials this time. Can you apply the faster way of getting the GCMF here? Can you get it mentally this time? You can pause this video to try it now. Go! What did you get? Here's the GCMF. I hope you got it correctly and fast. Let's continue the exercise and use this GCMF to factor the trinomial. Remember to divide the trinomial by the computed GCMF. Pause this video now to try it. Go! Here's the answer. I hope you got it. Here are more exercises. You can try them and pause this video now. Go! Here are the answers so you can check. We can go to the next video for part 2 of this tutorial series on factoring polynomials. Please don't forget to like and subscribe. Happy solving!